Hey everybody. Today we're talking about the geometric distribution, which models the number of attempts needed to obtain the first success in a sequence of Bernoulli trials, all of them with the same parameter p. For instance, flipping a coin or shooting free throws. Let's start just by doing an example, and you don't need any theory about the geometric distribution to do this, so I recommend trying this on your own before advancing. A child decides to roll a six-sided die, a fair die, until they obtain their first four. What's the probability that they need exactly 2 rolls? The probability that they need no more than 2 rolls. So if x is the total number of rolls that they need, then x equals 2 can happen only if the first roll is a failure and the second is a success. So a not 4 and then a 4. The probability is 5/6 times 1/6 by the multiplication rule for independent events. We get about 0.139. To find the probability that x is no more than 2, we're going to take the probability that x is 1, the probability that x is 2, and add those up. Those are the only 2 ways that the total number of rolls can be no bigger than 2. When we do that, we get about 30.6%. More generally, if the probability of success is p, and the probability of failure, 1 minus p, is called q, then the probability that the first success occurs on roll x is given by q to the x minus 1 times p. Because the only way that the first success can occur on trial x is if there are x minus 1 failures in a row, followed by a single success. And this is the probability mass function, or PMF, for the geometric distribution. F of x is q to the x minus 1 times p. The support is the positive integers, 1, 2, 3, etc. When you're doing calculations or proofs involving the geometric distribution, the formula for the sum of a geometric series comes up all the time. A geometric series being a sum that goes on forever, where each term is obtained from the one before by multiplying by a common ratio, called r. If a is the first term in that series, then the formula for the infinite geometric series is given by a over 1 minus r, which converges exactly when the absolute value of r is less than 1. This is sometimes called the fundamental identity of this distribution. Returning to that probability mass function and summing it up over the entire support, we apply that fundamental identity, that formula for the sum of a geometric series, to get p over 1 minus q, because here the common ratio is q, the first term of that series is p. 1 minus q is p, so all of this simplifies down just to 1. The probability that the first success will eventually occur is obviously 100%. And this verifies that that formula actually defines a legitimate probability mass function. One important warning is that the geometric distribution is also often modeled with a slightly different PMF, q to the y times p, where y can be 0, 1, 2, 3, etc. Here y is representing the number of failures before the first success rather than the total number of trials, including that first success. Now, I'm not going to use that formulation in this video, but it's so common that you really have to know both of these. You have to be able to recognize when one or the other is being used and apply it appropriately. But fortunately, translating between these two formulations isn't hard, because x is just one more than y. Y is the total number of failures, x is the total number of trials. There's exactly one success, so x is y plus 1. The cumulative distribution function of a geometric random variable is, of course, the probability that the random variable is less than or equal to the specified value x, whatever that specified value might be. So all we're doing here is adding up the PMF starting at the beginning of the support, k equals 1, and ending at that value x. We get p plus qp plus q squared p, etc. Now, this is a terminating geometric series. There's a formula for that as well, so this should have a simpler form. Now, I always forget the formula for a terminating geometric series. I always have to look it up. I think that's okay. The formula for the infinite geometric series comes up a lot more often and becomes a lot more important if you're dealing with the geometric distribution in a mathematical way. So hopefully that one gets stuck in your brain. If we apply that formula and then again simplify using the fact that 1 minus q is equal to p, we get big F of x equals 1 minus q of x, which is the formulation for the CDF that you see and use most frequently. This has a very natural interpretation. The probability that the first success comes in the first X trials is complementary to the probability of X failures in a row. Returning to that example with the child throwing that die until they get a 4, what's the probability that they need no more than 8 rolls? So here we're trying to do big F of 8. I have it written out with the sum there on the left, and then the simpler form, 1 minus q to the 8th, 1 minus 5/6 to the 8th, which is how I actually evaluated this, and I got about 76.7%. Following along with that example a little further, find the probability that the child needs between 4 and 10 die rolls, including 4, including 10, to obtain that first 4. So we are going to do f of 10 minus f of 3, because this probability is going to be the probability that x is less than or equal to 10, no more than 10 rolls, minus the probability that it takes 1, 2, or 3 rolls. We plug into that formula, we simplify it a little bit, we get q to the 3rd minus q to the 10th, 5/6 to the 3rd minus 5/6 to the 10th. It's about 41.7%. By the way, that third line, q to the 3rd minus q to the 10th, is the formulation for this sort of probability statement that's most important to you. The probability that the random variable is between a and b is going to be f of b minus f of a minus 1. The expected value of a geometrically distributed random variable is mu equals 1 over p. And the proof is really short and I think instructive, so I'm just going to flash it at you. I won't dwell on it long. We're trying to compute the sum over the support of x times f of x, which is p plus 2qp plus 2q squared p, etc. And while this isn't exactly a geometric series because of the 2, 3, etc., it is close enough so that we can use the standard trick, multiplying by a common ratio and subtracting the result from the original. Here's how it goes. I've written the formula for mu at the top, and then right below that, multiplied both sides by q. The third line there subtracts the second line from the first. So 1 minus q times mu on the left-hand side. And then on the right, we just have a geometric series, a familiar one in fact, p plus qp plus q squared p, etc., which simplifies to p over 1 minus q, which is just 1. Dividing both sides by p, we get that the expected value is 1 over p. The variance of a random variable with a geometric distribution is given by q over p squared. And I'm not going to do that proof. It's a little bit more involved. It's usually done using the moment generating function, which we haven't gotten to yet in normal knowledge probability. Let's return to this child with the die one more time. The child's rolling that 6-sided die till they get a 4. What's the expected number of rolls that they'll need? Also, what's the variance and the standard deviation? So in this case, p is 1/6, the probability of success. So the expected value, 1 over that, is just 6. If they're rolling that die till their first 4, on average, it's going to take them 6 rolls, which I think is kind of like intuitive. It might be what we would guess even if we didn't have any of this probability theory behind us. The variance, q over p squared, 5/6 divided by 1/36. Simplifying that, we get 30. And the standard deviation, the square root of that, is 5.48. So 6 rolls are expected, but there's a large amount of uncertainty in this probability experiment.